You ever wonder what the real secret ingredient is that makes our modern world, well, work? It's not the internet, it's not some fancy software, it's not even the microchip itself. No, it's this hidden engine, this entire field of engineering that quietly makes almost every single piece of tech we love possible. Okay, let's dive right in. Think about it. Your smartphone, an electric car, the massive data centers that are the internet, solar panels, high-tech medical gear. I mean, on the surface, what do these things even have in common? They all share this one fundamental critical dependency. They all need to take electrical energy and control it with just incredible precision and efficiency. And that, right there, is the job of power electronics. So what is this stuff? At its very heart, power electronics is all about taking electricity in one form and expertly changing it into another. It's about making electricity useful. You know, the power coming out of your wall socket is one thing, but your laptop needs something totally different. Power electronics is that crucial middleman that handles the translation. To really wrap your head around this, let's use a super simple everyday example. Okay, your car's charger port gives you something like, I don't know, 12 to 15 volts. But your phone, it wants a nice, clean, steady 5 volts. So how do you do that? How do you bridge that gap and get from 15 down to 5? Well, the most obvious way, the brute force method, really, is to just get rid of the voltage you don't want. You could use a component that kind of acts like a dam, a variable resistor. It takes in all 15 volts and then it just fights and blocks the flow until 10 of those volts are gone, letting the other 5 volts pass through. But here's the key question. Where do those 10 volts go? They're turned directly into useless waste heat. And this is where you see the huge problem with this method, which is called a linear regulator. You're pulling all this power from your car's battery, but only a tiny fraction of it is actually getting to your phone. The rest? It's just making your car charger hot for no good reason. It's just unbelievably inefficient. How inefficient are we talking? Well, for our car charger, going from 15 volts down to 5, the absolute best case scenario efficiency is a measly 33%. That means two-thirds of the energy you pull from your car is just gone. Poof, vanished into thin air as heat. And oh, it gets so much worse. Think about a modern computer processor. It needs maybe just 1 volt to run, but the motherboard is supplying it with 12 volts. If you use the same brute force method, your efficiency would crash to less than 10%. You'd need a giant fan just for the power conversion part. Your computer would basically be a space heater that, occasionally does some math. This is obviously it's terrible. It's not sustainable. It's incredibly wasteful. It creates a ton of heat, and it makes things like long battery life totally impossible. There's just gotta be a smarter, more elegant way to do this. And thankfully, there is. See, the whole problem, the villain of the story so far, is the resistor. By its very definition, its job is to waste energy as heat. It's designed to be lossy. So if we want to build a better converter, we need to use components that by their nature don't waste energy. And that brings us to the hero of our story, the ideal switch. The magic here is just beautiful, simple physics. Remember, power equals voltage times current. Well, when a perfect switch is on, current is flowing, but there's 0 voltage across it. So current times 0 is 0 power lost. When it's off, you have voltage, but 0 current is flowing. Again, 0 times anything is 0. In both states, it wastes absolutely nothing. It's a perfect, lossless component. So, how do we use this amazing switch? The idea is genius. Instead of burning off energy, we use the switch to chop up the incoming 15 volts into a series of incredibly fast on and off pulses. And by controlling exactly how long the switch is on versus how long it's off, that's a technique called pulse width modulation, we can precisely control the average voltage. If we keep it on for just 1/3 of the time, the average voltage becomes 1/3 of 15, which, hey, is exactly 5 volts. Okay, but now we've got a new problem. You're probably thinking, wait a minute, my phone can't run on a choppy, pulsating voltage. It needs smooth, constant DC power. We've got the right average, but it's in the completely wrong shape. How do we smooth it all out? This is where we bring in the switch's partners in crime, the inductor and the capacitor. And here's the key. Just like the switch, these components are also ideally lossless. They don't burn energy, they store it. An inductor is like a little energy piggy bank for magnetic fields, and a capacitor is one for electric fields. Think of them as tiny, ridiculously fast rechargeable batteries. And this right here is the fundamental breakthrough. This is the whole game. We completely changed our philosophy from just destroying unwanted energy to instead cleverly storing it for a split second in these components and then releasing it to perfectly smooth out those pulses. We're not throwing energy away anymore. We're just managing its flow through time. So, does this new, clever method actually work? Let's look at a hardcore, real-world example. A data center that needs to convert 400 volts down to 12. The old, wasteful, brute force way, it would be a pathetic 3% efficient. But our new method, the switched mode converter, an absolutely incredible 97% efficient. The difference isn't just big, it's staggering.
And this is what modern power electronics gives us. I mean, look at that. We're getting so close to perfect. Almost every drop of energy we take from the source gets delivered to where it needs to go. That tiny 3% of loss, that's just the real world creeping in, because our components aren't quite ideal, but wow, are they close.
Now, you might be thinking this is all for big industrial stuff. Nope. Let's bring this right back to the phone that's probably in your pocket. According to MIT, a mind-blowing 40% of the circuit board area inside an iPhone is dedicated to just this, tiny, hyper-efficient power converters. It's like a whole city of miniature power plants all working together just to keep the lights on.
And this isn't just some cool engineering trivia. This efficiency changes everything. Less wasted energy means less heat. Less heat means you don't need giant fans and heavy metal heat sinks. That's what lets us make devices that are so small and light. It's the secret to amazing battery life. It's the absolute core of an electric vehicle's powertrain, and it saves literally mountains of energy and money in the data centers that run our lives.
Power electronics really is the unsung hero of our time. And as we push forward into a future that's going all electric, smart grids, renewable energy everywhere, electric cars, the need for even better, even faster, even more efficient ways to control electricity is just going to explode. This hidden engine isn't just powering our world today, it is literally building the foundation for the world of tomorrow.